All right, guys, now that we've spent time looking at similar triangles, seeing how we can set up proportions with similar triangles, determine triangles are similar, we're going to do a little bit of application here of how these could be used. So learning goals here, identify similar triangles to calculate indirect measurements. So an indirect measurement is something we can't directly measure. We can't put a tape measure on. Use similarity to solve for unknown measurements. All right, me and my shadow. How would you measure the height of a flagpole? Again, something that's not as easy to measure. Okay, we can't take a direct measurement of a flagpole or the height of a very tall building. So we use this idea of indirect measurement, where we use similar triangles in order to determine the height or the distance of something that would not be easily measured by hand. Okay, so we got first a little video within a video here. All right. So hopefully that gives us a little better idea of this here. This idea of an incident ray, a reflected ray, and then particularly the angle of incident and the angle of reflection. And again, the main thing we want to get out of that is that those angles are going to be congruent to each other, because that's what's going to allow us to set up similar triangles in a lot of these situations and then be able to set up our proportions in order to be able to solve. Okay. All right. So this first situation here is, say we wanted to measure the flagpole. We wanted to know how tall the flagpole was. So it kind of goes through some steps you could follow, and this could be for any tall object here, to be able to set this up. Okay. So it says here, you got a mirror. You put a dot in the center of that mirror. You're going to put that mirror on the ground. It says here you're facing the object. Okay. And then you want to put that, obviously, the mirror between yourself and the object there, all of those things in a straight line. That's the collinear piece there in step 2. And then you're going to look at that dot and walk backwards until you see the top of that object, in this case, the flagpole. You see the top of that flagpole right on the dot. All right, so then if we kind of sketch what we are looking at here, this is what we would have. Your eyes looking down into the mirror. Again, that angle of incident and the angle of reflection. The angle of incident would be coming from the flagpole. The angle of reflection up to your eyes there. We now know that those angles are going to be congruent to each other. Right angles there where you are standing and then where the flagpole is. So this gives us two similar triangles by angle, angle. We don't know the measure of those two angles of incident and angles of reflection, but we don't need to. We know that they are congruent. Okay. And we see, some of these things would be easy for us to measure. We could measure our height easily. We can measure our distance to the mirror easily. And we can measure the distance from the mirror to the base of the flagpole easily. So if we take those measurements and put them on our diagram here, so let's say, for example, these were our measurements. Height of the person was 5'3". They're 6 feet from the mirror, and the distance from the mirror to the base of the flagpole is 10 feet 6. Okay, so we can now use these with our similar triangles to set up a proportion that we can solve. So the h over the 5'3" equals 10'6" over 6 feet. Now, before we solve this, one important thing we need to make sure to do is convert these from feet and inches into decimals. So, what part of a foot is 3 inches? What part of a foot is 6 inches? So we get, 5'3" is 5.25 feet. 10 feet 6 inches is 10.5 feet. Now we can cross multiply. Divide by 6 there, and we get a height of 9.1875 feet. Okay, again, now we want to go back to see how many feet and inches that is. So a little reminder here in Desmos. So 9.1875, well, let me take the full 9 feet off. So subtracting 9, that leaves me with just the 0.1875. So that's the part of a foot I have. There are 12 inches in a foot, so if I multiply that by 12, I get how many inches? So 2.25 inches there. So that's 9 feet, 2.25 inches, 2.5, or we can say approximately 9 foot 3 inches there. Okay, so just kind of some more examples here, some more practice with this. First off, we're going to calculate the height of this tree. You can see this is Maureen here. She went to the park. She used the mirror method as well. She's already got her measurements there. So there's our height that we want to find. Okay, note there on the bottom, the 16 feet is all the distance from her to the base of the tree. So we had to subtract 4 from 16 to get the distance from the mirror to the tree there. So now we can set this one up. H over 5.5 equals 12 over 4. So that's using our similar triangles to set up a proportion there. Cross multiply again, and we get a height of 16.5 feet. Okay, another one with a mirror, setting up the similar triangles a little differently here. Stacy notices that another tree casts a shadow and suggests using shadows to calculate the tree's height. She lines herself up with the tree's shadow so that the tip of her shadow and the tip of the tree's shadow meet. So we see here another way of setting up similar triangles. Again, similar by angle, because they both have a right angle here, and they both share this angle. So those are going to be congruent. So again, similar by angle. Height of the tree, which she's trying to find. Again, note here, this piece is 15, this piece is 6. So the entire base of this triangle would be 21 feet. So if we're looking at the big triangle versus the little triangle, we need this entire piece down here for 21 to set up our proportion. So now we've got h over 5.5, so this height over Stacy's height, and then 21 over 6, so the base of the big triangle over the base of the little triangle. Again, comes down to cross multiplying, divide by 6, and we get a height of 19.25 feet here. Okay, again, just another situation. So this one here, I think, helps to highlight this problem would be really difficult if I didn't have this picture. If we were just given this, which in a lot of times on a Delta Math assignment, or maybe in Mathia, or certainly on an assessment, you're just given the words. You're not given the picture that goes along with it. But note how the picture and being able to label these pieces, label these distances on our picture, make this problem a lot easier. So this serves as a reminder. Don't be afraid to draw pictures out. Okay, label where things are. It makes it a lot easier to see your similar triangles. They're both right triangles, and we have congruent angles of incidence and angles of reflection down here. So that allows us to see our similar triangles to set up our proportion to find the height of this volleyball net. Cross multiply, height of the volleyball net is 7.5 feet. Okay, this one here allowing us to indirectly measure the distance across a ravine. Okay, again, we can see how this one is set up. We've got Rachel and Gavin here. They measured, their spots from the edge of the cliff. Gavin is 8 feet away. Rachel is 6 feet away. And then this length here in order to create their similar triangles with these vertical angles here. Okay, so this distance, Rachel from this point is 15, and then Gavin is 60. Okay, so this is what we're trying to find, this width of the ravine. So note here, the big thing to note is this bottom of this triangle, as we see here, we have to have the width of the ravine plus this 8 feet here. So W plus 8, that is the bottom of this big triangle, over 6, the bottom of the little triangle. 60 over 15, that's the heights of both of the triangles. Again, when I cross multiply, make sure we distribute the 15 times the W and the 8. All right, so as I do that, we end up here, 15W plus 120 equals 360. Subtract 120, divide by 15, and we see this ravine has a width of 16 feet. Okay, that is it for our application problems.